Natalie and Pat are our presenters today. We will start off with Pat, and we will take questions after Natalie's presentation, which comes second. So to have more time for the talks, and then they talk also on similar topics. So it will be nice to have a challenging discussion. Let me briefly introduce Dr. Pat Wongpan. Pat is a research associate with the Australian Antarctic Division at the University of Tasmania in Hobart, Australia, where he works as a quantitative sea ice biochemist and ecologist within the sea ice program there. And I want to give a shout out to Pat, who in 2023 received the IGS Early Career Scientists Award. So well done, Pat. His interests, as you will see from his talk, are investigations of physical and biogeochemical drivers in the sea ice, including the ice algal biomass evolution. And he works very much in numerical modeling, extensive 1D, but also 3D modeling. And he has a keen interest on the primary production, especially in the Southern Ocean. So Pat, please take it away, roughly 20 to 25 minutes for you. Thank you.
Yep. Thank you very much, Petra. Yep. Can you see the first slides? Okay, Petra and everyone?
Yes,
yep.
View is perfect. Thanks.
Okay, thank you. Thank you very much, everyone. And it's a pleasure today to present to the IGS community as part of the global seminar. Good morning, afternoon, evening in your time zone. I'm Pat Wongpan. As Petra mentioned, I was the quantitative sea ice biogeochemist and ecologist. Now I'm a coastal Antarctic remote sensing, which is the interim position, inspired by this work. And now I look a bit more into the remote sensing aspect of the sea ice and the coastal ice cape. Today, we're going to talk about the Antarctic landfast sea ice, a model-based estimate of its gross primary production. And if the time allows, I will also mention the upcoming challenge, and that could be a good bridge to the next talk by Natalie Robinson. I also would like to acknowledge all the contributors to this talk. And I saw, quickly the Matt Cockhill and others may be joining this session. So thanks a lot for all your contribution. On your right-hand side, this serves as a graphical abstract. As you could see here, this is the evolution of the landfast sea ice that painted with the orange color. And this, the bathymetry and the ice sheet and all the ice cape taken from the bed machine by Mulligan et al. In 2017. The key aspect of this work is we combine the fast ice distribution dataset with the one-dimensional sea ice physical biogeochemical model called LIM1D. This combination allows us to estimate the total primary production in landfast sea ice for the first time. Before I'm going to my science, here I'm presenting from Hobart, so I would like to acknowledgement of country. Today I'm presenting on Lutruwita, or Tasmania Aboriginal land, sea and waterways. I acknowledge with deep respect the traditional owner of this land, the Muwinina people, and I pay my respect to elders past and present, and to many Aboriginal people that not make elder status, and to the Tasmanian Aboriginal community that continue to care for country. And the photo on the right is Clifton Beach near Hobart, looking toward the Southern Ocean. And just a brief history of myself. Until now, I'm from Thailand originally. I did my master and PhD in New Zealand with Pat Langhorne, Inga Smith, and Dave Pryor at University of Otago. And I joined Antarctic expedition during my PhD at Scott Base and also at Davis Station, also with Petra Heim in 2015. And we did this observation, the measurement of the light transmission through snow, sea ice, and absorbed by sea ice algae. And that gave me an opportunity to work with Dr. Klaus Meiner, my advisor, who introduced me to this aspect of sea ice algae. Did some experiment with sea ice orientation in New Zealand, and did some permeability work in the UK with Gerald Neufeld. And I finally finished the simulation work of this subice layer, which you could see on the right, physical model only. And this could be a good bridge to next talk by Natalie Robinson. And recently lucky to join the 4-month expedition with the Japanese program to conduct the observation of fast ice at the Showa station, and back here now in Australia to work on this simulation of the sea ice algae in the fast ice that I'm presenting to you today. The outline of this talk, I will follow this loop to also understand the distribution of crowded iceberg, then it could help improve the understanding of the Landfast sea ice distribution. And my contribution so far in the fast ice could be more and more important, and thanks in particular to Dr. Alex Fraser, where we joined the force and with other fast ice enthusiasts to with the on the also high reader to know more about the role of side, but give to him. There, and also, last year and this year we have a problem. As we all know, the Antarctic sea ice extent has plummeted throughout 2023 and 2024. And thanks to Petra, now we have the nightlash.org that you could explore this difference on the sea ice extent. And I provide a QR code in case you would like to explore. But it's not only the sea ice in total, but also for the fast ice, where you could see the very strong decline recently. And this published in our review of geophysics review since around 2020 now and continues to decline. Another piece of information before setting up the problem of this study is if we look at the contribution of the primary production in the Southern Ocean, which is the formation of organic matter by photosynthesis. And this process is very important that the energy enter this polar marine food web. And for sea ice, we measure this amount as a teragram carbon per year, which is a 10 to the 12 gram of carbon per year. But the most important thing is not all this primary production can be observed by satellite or today's BGC Argo, thanks to the snow that cover this algae in sea ice. So this part, we still have to do the traditional way, like the coring method, or can be upscaled by modeling to assess this evolution of the sea ice algae in the sea ice and approximate its primary production. Putting the problem of the sea extent together also with the primary production that contribute by the sea ice, the research question is how this increased variability of the sea ice extent and the fast ice extent could impact the sea ice or the fast ice ecosystem. So to assess or to help answer this question, we need a reference value or the baseline of the primary production in Antarctic landfast sea ice. But if we look into the literature, there's a big gap here for the Antarctic fast ice. We did not know the value of its total primary production, but it's mainly because we also didn't know about the distribution of fast ice before Alex Fraser published this fast ice distribution. So combine this together and we pick a year 2005, 2006, which is also a mean state of the fast ice extent, as you could see here from the time series of its extent. And the previous work by Ben Sainz and Kevin Arrigo, who estimate the primary production mainly in the packed ice area that has a value of about 23.7 teragram carbon. So if we conduct the simulation that year, we could assess the contribution of the fast ice primary production to the total CI primary production. But to digest to many audience, also in the public, why we have to care about the fast ice and why we have to simulate this fast ice primary production. The effort from Klaus Miners in 2017, if we combine all the area of the ice core together, 1970, it's just about 5.65 square meter, or that's about 0.001% of the football pitch. From Alex Fraser, sea ice extent is about 600,000 square kilometer. So what we know is just that portion of football pitch. But the whole area of fast ice is about 84 million football pitch. So we have to understand this big piece of the fast ice cover. And yeah, I'm a big fan of Ted Lasso, and I like to say that the fast ice is life when you look closely and you see the sea ice algae, or when you do the ice core and you see the brown piece of it. So the fast ice is life, and we look how the nature, physical, biological parameter control this life. And obviously, we reconsider this video. We see the snow on top. We have the ice thickness. Then this control the amount of light, the temperature, salinity, and the connection with the ocean underneath. That also control the nutrient, and also the history of the sea ice, how it grows. They also have some trapped nutrient in the structure. And this all together control the life in sea ice or in the fast ice. And just a quick mention why the sea ice algae is important, because it is a crucial bridge between the low and high productivity period, in particular in the polar marine food web, especially in winter, where, for example, the larval krill can graze on this fast ice underneath the sea ice algae. And today, you look through the simulation result, and this is how we plot the sea ice BTC modeling result from the ice that formed to the end is evolution when the sea ice growing, as you could see on the right from the experiment. And then on top, we have the snow, and then we have the ice algae grow at the bottom when the condition is right, light, bright, salinity, and the temperature all together. Yep, and so today you will see a lot of this plot that look like this. Due to the time limitation, I'm not gonna go too much into the model, but for any person who interested, it's described in Van Coppeno and Tedesco in the CIS book in the 3rd edition, and be revised soon for the 4th edition. And parameterization we use from Lim et al. 2019, and our model, the growth of the quasi algae controlled by temperature, light, bright salinity, macronutrient. But due to the lack of observation and outer limitation, we do not include the platelet ice or the subaqueous layer as part of this estimation. As you can see later on, this make our value could be underestimated after you see the brown stuff from Natalie Robinson in the next talk. And just to say quickly that not only the parameter that limit the growth of the fast ice algae that I mentioned, the key limitation after we have the fast ice distribution is the definition of the fast ice itself. So from the data set, when we combine with the satellite remote sensing data, we could track that is a fast ice or not to be included at the fast ice primary production estimate. So I could say overall the fast ice distribution is the main limitation of the estimation of its gross primary production. And because our grid cell is quite big, so inside the grid cell, we also have multiplication factor for the snowfall. Then we can take care of the sub-grid scale variability of the snow distribution. And as you can see here quickly that the influence of snow, when the snow is too thick, basically the sea ice algae could not grow. When snow is thin, the sea ice algae grow really well. And you can observe the spring bloom and the autumn increasing of the sea ice algae. Yeah. And I don't have much time left, so just to say how we're gonna display the result of this fast ice primary production, and that inspired by the coastal life. And this is the population distribution of Australia. And this is the main result that we end up with the distribution of the fast ice primary production for each grid around Antarctica. And just to give some sense of this teragram dimension, so 0.0101 teragram is weight about of the 2000 cows. So we could estimate its value. And I just come to the main result. And basically, as I mentioned here, the evolution of the fast ice control the growth, control the estimation of the primary production for each grid cell. And then we integrate and combine together. And another limitation, we didn't know much about the multi-year fast ice, so we have to correct that fraction as well, because in our simulation, all the sea ice treated as the first year fast ice. And from our control run, we also look at other setup or different in terms of the parameterization and the forcing, and putting all together, we came up with the mean of 2.8 teragram carbon per year. And this is about 12%, which range from 5 to 19% of the total ice algal productivity. So we accomplished our aim to put the number of 2.8 teragram carbon per year back into the table. We could also look into the ratio of the primary production per area when we compare between fast ice and pack ice. And for each region around Antarctica, we got the mean of about 3.3 times of the fast ice primary production per area, which is higher than that in pack ice. And this is my graphical summary, combining the modeling with the fast ice distribution in the 2D. Then we get this estimation of the primary production in the fast ice, and it's about 12% of the total ice algal productivity. And I just spend maybe just 1 or 2 minutes here before pass the presentation to Natalie Robinson. There's some upcoming challenge when I start working on this, and I would like to mention the importance of the grounded iceberg, as I mentioned before in the introduction. And now I'm providing the distribution of grounded iceberg to the simulation of the fast ice by Dan Water, Alex, a PhD student. And from what I saw, it helped improve the fast ice extent distribution when you include the grounded iceberg. And with Geosci Australia, with Laurie Padman and Susan Howard, we are also working on the grounded iceberg distribution dataset. And it's still work in progress, but we hope we could submit that soon to the Earth System Side data. before the end of this year. And finally, what I could not include in this study is this thunderstorm or snowstorm under sea ice, this platelet ice. We need to have the ice shelf water at the right place at the right time around Antarctica. And yeah, would like to get this water column and finally could include this survival layer into the future estimation of the work. Because we already have the physical model, we can form this in the sea ice 1D model. And with the work that Natalie and the team have been working on in the future, we could have the complete fire simulation and with this survival layer included. So that's future work. And yeah, thank you. And next to Natalie with this penguin colony from Cape Roy. So Natalie will join us live from Antarctica. So thank you, everyone. And sorry, I'm a bit over time. Thank you.
Thank you very much, Pat. Was very interesting, and passing neatly to Natalie. We take questions for both speakers after Natalie's presentation. Very quick introduction to Natalie. She is a marine physicist with NIWA, the National Institute for Water and Atmosphere in New Zealand, and also holds a joint appointment with the Antarctic Research Centre at the University Victoria in Wellington. She's currently the Deputy Director of the New Zealand Antarctic Science Platform, where she leads the stakeholder consultation and co-design of the platform research plan for 2025 to 2032. And next July, she will become the director of this New Zealand Antarctic Science Platform. So Natalie, I hope your connection from Antarctica holds. We look forward to your presentation. Thank you.
Kia ora, everyone. Petra, can you just confirm that you can see my screen and hear my voice?
Both fine, thank you.
Wonderful, thank you very much. And thank you for the wonderful presentation, Pat. You've said a lot of things that mean I don't have to say them now. And really the synergies between our two projects are wonderful. So I'll be tapping you on the shoulder in due course. So, yep, I'm currently conducting fieldwork on the sea ice of McMurdo Sound. I really agreed to do this seminar because we were having Starlink in the field for the first time. So, very much a work in progress, as you might appreciate. Really show and tell, but more show than tell. So, as Pat mentioned a few times, the focus of the study we're doing at the moment is the layers of platelet ice that form beneath the fast ice in the immediate vicinity of cold ice shelf cavities. And it's a truly interdisciplinary effort with a host of both biological and physical disciplines involved. So just a quick introduction. When warmer water comes in off the continental shelf and interacts with the base of the ice shelf, it generates a little bit of fresh water that is added to the water column. But it's added at the depth of the base of the ice shelf. So, you know, anywhere from 100 to 500 or 700 meters deep. And so that slightly fresher water wants to rise through the water column, but all it can do is follow the base of the ice shelf up. And as it does so, it is being subjected to less and less pressure. Obviously, it's rising through the water column. And so at the point where we observe the water, so we work on the sea ice that is immediately at the front of the ice shelf. And so by the time that the water reaches us there, it has become super cooled. So it is below its own freezing temperature, below the local freezing temperature. And that is a result of not a change in temperature or salinity of the water itself, but of the pressure affecting the local freezing point. And so that gives rise to these layers of platelet ice. So here's an example of a single crystal of platelet ice, which begin as tiny seeds of ice that are suspended in the supercooled water, and they'll grow until a point where they become sufficiently buoyant that they can overcome the turbulence in the water, and they'll precipitate up to land against the base of the sea ice. And in a single year, these layers of individual crystals can form several meters thick. We've had up to 6 meters. Here we are here. And so these, it's very difficult to get images like these, so I don't have a lot of them. So as the crystals accumulate, they sort of land in random orientations, but because they're still surrounded by supercooled water, they can continue growing and in fact grow through each other to form a porous lattice type structure that's sitting underneath the sea ice, which is pretty robust when it's in the water because all the interstitial spaces are filled with water. But as soon as you try to extract it and the water drains out and replaced by air, of course the density difference between the ice structure and the water and the air is sufficient that they become very fragile and disintegrate. But hopefully you get the idea that we have quite a unique habitat here. So these interlocking crystal structures with water that is able to flow through them provide quite a quiescent and protective environment for any life that finds its way into it. So looking at the image on the left, this is McMurdo Sound. So you have mainland Antarctica running up the left-hand side of the image, with Ross Island forming the eastern side of McMurdo Sound. And this, coming up the western half of McMurdo Sound, is a significant outflow of ice shelf water ultimately sourced from beneath the Ross Ice Shelf. And so that's our location of interest because that's where the supercooled water is at its highest concentration and volume. And of course that supports the largest platelet accumulations in the area. However, we were rather hampered by our conditions. So our first opportunity to actually sample the platelet layer quantitatively came in 2022. So if you look at the image on the right, this is